In the dark water below a shipping lane, a machine moves without a crew, without windows, and without a constant connection to command. It listens, not for voices, but for pressure changes, propeller signatures, magnetic traces, and the faint geometry of the seabed. This is HiTechnomy. Look beneath the surface of the future. Powered by Alligence Labs. If it finds a mine, a cable, a submarine, or a warship, the most important decision may not happen underwater. It may happen in the gap between what the machine detects and what humans can understand in time. In this episode, ghost fleets, unmanned submarines, autonomous surface vessels, and the machine networks beginning to reshape naval warfare. Aircraft carriers, nuclear submarines, destroyers, and crewed patrol aircraft still matter enormously. They carry weapons, people, endurance, judgment, and political meaning. But around them, a new layer is forming. Small underwater drones search harbors. Larger unmanned vehicles map the seabed. Surface drones relay data. Seabed sensors watch choke points. Software fuses fragments into a tactical picture. The future fleet may not be one giant ship. It may be a distributed nervous system spread across the ocean. Imagine a naval planner watching a maritime operations screen during a crisis. The map is not empty, but it is incomplete. A destroyer reports one contact. A satellite passes overhead, then disappears beyond its orbit. A crewed submarine remains silent because silence is survival. Commercial ships create noise. Weather distorts the surface. The seabed hides cables, sensors, pipelines, and places where machines can wait. This planner faces a basic problem. The ocean is too large, too deep, and too opaque for humans to monitor continuously. For more than a century, naval power has depended on exquisite platforms, battleships, carriers, nuclear submarines, guided missile ships. These systems are powerful, but they are expensive, limited in number, and difficult to replace. Unmanned naval systems offer a different logic. Not one perfect platform, but many distributed ones. A small UUV can inspect a harbor. A medium vehicle can scan for mines. An extra-large UUV can carry modular payloads over long distances. A surface drone can act as a scout, decoy, or relay. A seabed sensor can become a tripwire. None of these replaces a nuclear submarine, but together they extend presence. The bottleneck is not only hardware, it is communication. Radio waves die quickly in salt water. A submerged vehicle cannot simply stream video to a satellite. Acoustic modems can send data through sound, but slowly, with limited bandwidth, and through an ocean filled with noise. So the machine must often continue without asking permission every few seconds. That is why autonomy underwater is not a luxury feature. It is the price of admission. A ghost fleet is not one machine. It is a system of systems. At the platform level, unmanned underwater vehicles range from small torpedo-shaped drones to extra-large autonomous submarines. Some are built for mine detection, some for ocean mapping, some for intelligence, surveillance, or undersea infrastructure missions. An XLUUV, an extra-large unmanned underwater vehicle, is essentially a modular autonomous submarine without a crew. Its body can hold batteries or fuel systems, propulsion, sonar, navigation hardware, a mission computer, and a payload bay. But the brain matters as much as the hull. Underwater autonomy has to solve navigation without reliable GPS. It may use inertial systems, Doppler velocity logs, terrain relative navigation, acoustic beacons, and occasional GPS fixes when near the surface. It has to fuse sensors, sonar returns, magnetic anomalies, optical glimpses, current data, and acoustic signatures. A rock, a mine, a marine animal, and a small submarine may all appear as uncertain patterns. It has to adapt. If a current pushes it off course, if an obstacle appears, if the mission area is noisier than expected, the vehicle must decide whether to reroute, slow down, surface, send a buoy, or stay silent. This is the central shift. Naval autonomy is not mainly about removing people from war. It is about extending human intent through an environment where human control cannot travel easily. The machine is not free because navies want less responsibility. The machine is free because the ocean refuses constant conversation. Surface drones complete the architecture. A USV can patrol above a submerged UUV, act as a communications gateway, tow sonar, or pass compressed data to satellites. It remains on the surface. The UUV works below it, usually with far less bandwidth and far less visibility. Buoys, aircraft, crewed ships, and command centers become part of the same network. But this network is not omniscient. It is delayed, uncertain, and probabilistic. The best systems will not know everything. They will know enough at the right moment to change the decision space. In the laboratory, autonomy can look clean. Routes are simulated, targets are labeled, conditions are bounded. At sea, the ocean edits the plan. Launch and recovery can be difficult. A large, unmanned underwater vehicle may require a port, a support ship, specialized handling equipment, or calm enough conditions to bring it home. Batteries limit speed. Sonar can reveal the vehicle's presence. Surfacing to communicate can expose it. The naval planner from earlier does not receive a perfect live feed. Instead, the planner may receive a compressed report, location estimate, confidence level, contact classification, battery state, and recommended next action. That report may arrive late. It may be incomplete. It may ask humans to make a judgment based on uncertainty. Real-world programs show the direction of travel. The U.S. Navy's Orca XLUUV represents a move toward large, modular, unmanned undersea platforms. DARPA's Sea Hunter showed how an unmanned surface vessel could support long-duration anti-submarine tracking concepts. Australia's Ghost Shark reflects allied interest in long-range autonomous undersea capability. China has publicly displayed the HSU-001 Large Displacement UUV. Russia's Poseidon sits apart as a nuclear-powered, nuclear-armed autonomous underwater weapon, a strategic system with destabilizing implications. And in the Black Sea, Ukraine's use of unmanned surface vessels has shown how relatively inexpensive maritime drones can impose serious costs on larger warships. These are not the same class of machine. A small surface attack drone is not an extra-large underwater vehicle. One skims the waves, the other disappears beneath them. But together, they show how naval power is spreading into cheaper, more distributed, more autonomous forms. The ocean is becoming a battle space of unmanned scouts, relays, decoys, sensors, and potentially weapons, all operating around the limits of communication. Autonomous naval warfare has a hidden weakness. The same systems that make it powerful can make it fragile. Algorithms can misclassify. A seabed formation can look like a mine. Marine life can complicate acoustic signatures. Commercial traffic can create false patterns. A decoy can be designed specifically to confuse the model. Communications can fail. Acoustic links are slow. Optical links are short range. Satellite links require exposure. Jamming, spoofing, malware, and deceptive acoustic signals can turn the network against itself. Energy is another constraint. Moving faster drains power. Running active sensors may reduce stealth. Carrying more payload can reduce endurance. Every design becomes a trade-off between range, sensing, speed, silence, and mission complexity. Defenses will evolve quickly. Ports may use passive acoustic arrays, seabed pressure sensors, magnetic detectors, physical barriers, patrol USVs, and hunter-killer UUVs. Cable landing sites may become guarded zones. Choke points may be watched by networks that do not sleep. The future will not be autonomy versus humans. It will be autonomy versus counter-autonomy, with humans responsible for what both sides unleash. Modern life runs through the seabed. Undersea fiber optic cables carry the overwhelming majority of international data traffic. Offshore energy systems, pipelines, military sensors, and communications nodes sit in a domain most people never see. Unmanned systems can inspect and protect this infrastructure. They can map cable routes, search for tampering, and monitor approaches to critical sites. But the same capabilities can be used to threaten, probe, or signal. If a cable is damaged, who did it? A state actor? A commercial accident? A malfunctioning autonomous vehicle? A deniable operation? In deep water, attribution is slow. In a crisis, slow attribution can be dangerous. International law was not written for fleets of autonomous machines making decisions in contested undersea spaces. Existing maritime rules still matter, but many edge cases remain unresolved. There is also a paradox of escalation. Because unmanned systems do not carry crews, leaders may be more willing to send them into risky zones. That can lower the threshold for confrontation. But losing a drone is not the same as losing a ship full of sailors. In some moments, unmanned systems may give leaders an off-ramp instead of a funeral. A ghost fleet can absorb risk. It can also normalize it. The decisive question is how much judgment humans can keep when distance, speed, and silence push decisions into software. Return to the naval planner. A UUV detects an unknown object near a cable corridor. The AI assigns a confidence level. The system recommends shadowing, reporting, or engagement under pre-approved rules. The acoustic message is delayed. The object changes course. Human control still exists, but it is compressed into doctrine, mission design, rules of engagement, software testing, authorization chains, and the decision to deploy the machine in the first place. That is where responsibility moves, not only to the moment of firing, but to the architecture that made the moment possible. Here is the thought experiment for the age of ghost fleets. If an autonomous submarine spends 30 days alone in the dark, following orders written by humans, adapted by software, and interpreted through uncertain sensors, when it finally acts, whose judgment is it carrying? The future ocean may be more monitored, more defended, and more contested, but it will not be clearer. It will be deeper in every sense. If you enjoy deep dives into the technologies shaping our future, consider subscribing to HiTechnomy. This is HiTechnomy. Look beneath the surface of the future. Join us next time as we explore another technology, system, or breakthrough shaping our world. Powered by Alligence Labs.